So before I explain an edge-triggered D-type flip-flop, I need to explain a more basic flip-flop circuit. So this really is a basic circuit which is used in memory as it is capable of storing and retaining a single bit of data. So this would be an example of volatile memory like RAM because it requires power coming in, but assuming it's got power with logic gates, you can hold bits of data. All right, so to show you one of these workings, this is a basic flip-flop. Okay, here's an example one. I know it uses slightly different gates, but instead of using a NAND gate, it's designed with an AND gate and a NOT gate. It's exactly the same thing. Okay, so what we've got here is we've got two outputs, one signaling that this is our bit of data. Okay, so at the minute this is 0. This is our switch, which I'm going to show you switching on and off, and this is our clock signal. So our clock signal is going to continuously tick. You know about a clock ticking in the computer. So our clock signal is going to tick on and off. So what happens is if I turn this switch, my clock signal is going to continue to switch here and there. So every time there's a clock signal, I've got the chance of changing that data. Okay. So you notice that when the clock signal's off, I can't change the data, look. So it waits until it switches on and then it swaps. All right, so can you see that? So look, if I switch it, it's waiting until it's on before the data actually switched. But every time the clock signal switches, basically I've got the chance of whatever this input is, if this input's a 1, I've got the chance of changing that area of memory to a 1. So if I do it when it's off, next time it's on, that's now changed to a 1. And that will stay changed to a 1 until I choose to change my switch. Okay, so if I want to switch that off, I can. And then next clock tick, it switches off. And it will continue to stay switched off. So I'm continuously outputting a 0 now on every clock tick. For every clock tick, I've got the chance of changing that data if I want to. That's a flip-flop. Okay, so flip-flop is a very basic form of using logic gates for memory. So if we go back to the slide for a moment. So specifically, the thing I need to talk to you about is an edge-triggered D-type flip-flop. So it's a slightly more complex version of a flip-flop. So it looks like it does on the left. You don't need to necessarily be able to build this. You can do, and that website I was using was logic.ly/demo, which is quite cool. It's probably the best one I've found at this point. And this circuit basically takes a normal input and a second input being the clock. So I did try and recreate some of this in that example I showed you there. But this means that on each pulse of the clock, this flip-flop will change state. So every pulse of the clock, this flip-flop will have the ability to change its state based on the first input. Okay, so this means the data coming in will be stored in the flip-flop and continue to be output until the next trigger pulse is received, and then it again will take on whatever state this data input is. So if the data input is still a 1, the output will still be a 1. If the data input's a 0, the output will become a 0. And this clock tick, every clock tick, this will change. Okay, so it's a form of memory. It's a more extended version of the basic flip-flop on the previous slide. It's got a similar relationship to the half adder has to the full adder, but just remember the edge-triggered D-type flip-flop is a form of memory, can be used to store bits of data through a logic gate circuit. And remember, the two inputs are your data input and your clock input. And every pulse of the clock, you've got the ability to change the state of the output.